All right, welcome everyone for joining today's event. I believe that we have an exceptional session planned for everyone. Today, you'll have the opportunity to not only hear from some of the leading industry experts, but we've also prepared for everyone an opportunity to see a real life solution and see the entire life cycle of that end-to-end solution as well. So we're extremely proud of having the opportunity to present to you guys today. So just by way of agenda, so that everyone is aware, as I mentioned, we will start off today's session by providing a real-time demonstration of our hand activity recognition solution. This will be led by Daniil, who is responsible for machine learning here at Newton. After this particular demo, then I'll have an opportunity to give you guys a little bit of an overview as to how we were able to accomplish this solution. And then joining me, I'm extremely proud as well to have Arduino here. Andrea will also then give you guys an overview as to the latest updates at Arduino. Followed by Andrea, then we'll also have ZG, who will give some insight or provide some insight as to what's going on at Bosch Sensortec. And then last but not least, we'll bookend today's event with Daniil providing instructions or an overview as to how you can go through and create your own particular solution as well by leveraging the platform and, of course, by continuing to leverage some of the devices that we'll share with you guys at the end. We'll then close things out with a Q&A. So you have an opportunity to ask any of the members of today's discussion, any questions that you might have. And then lastly, as Julia mentioned, we'll have the opportunity for a giveaway. So it's not listed on the agenda, but at the end of today's event, don't forget the giveaway. So by way of introduction, I'd like to welcome ZG. So ZG is a sensor engineer from Bosch Sensortec. During his 10 years with Bosch Sensortec, he has experience in multiple roles, such as an embedded application engineer, developing embedded software solutions, including drivers, middleware, algorithms, and applications around MEMS sensors from his organization. As a customer solution engineer, helping customers with troubleshooting, optimizing, as well as custom development. And most recently, a business development engineer collaborating with hardware and software partners, creating reference designs or joint solutions to help customers from different market segments to remove barriers or reduce frictions in integration of sensors into their application, especially in the much diverse IoT field, which we'll be kind of discussing today. So I'm extremely happy to welcome ZG, as well as to have Bosch as one of our partners, as you will see today. Joining as well is Andrea. Andrea is head of the Pro Customer Success team at Arduino. The role of the team that he's responsible for is to provide solutions to companies that want to integrate and leverage the different Arduino solutions into their business. He's extremely passionate about technology as well as music. Andrea joined Arduino in 2014. Before this role, he served as a product manager for hardware department, pro business unit manager, and hardware production manager. Before joining Arduino, he served for 20 plus years as an ICT telco manager, network engineer in multinational companies. So welcome, Andrea. Extremely happy to have you with us today. Last but not least is Daniil. Daniil is responsible for our machine learning organization here at Newton. He's a full stack machine learning engineer. So if there are any questions, certainly that you guys may have at the end of the event, he certainly is the one that will be able to answer for you. He has over 8 years experience in this particular field. Before joining the Newton team in 2019, he executed various end-to-end complex machine learning projects in multiple domains in telecom, networking, retail, manufacturing, marketing, fraud detection, oil and gas, engineering and NLP. As head of machine learning and analytics at Newton, Daniel is working on the development of an automated TinyML platform facilitating sensor and audio data processing. He's an active contributor to the open source community with over 60,000 active users of tools features in his repository. As an inspired writer, Daniel publishes articles popularizing data science and introducing new methodologies for involving engineering tasks. Last but not least, I'd like to introduce myself. So my name is Blair Newman. I'm the CTO here at Newton. I'll be kind of, let's say, helping everyone navigate throughout today's discussion. And to begin things off, or to start today's discussion, I will hand it over to Daniel, where he'll begin to provide you guys an overview of the demo, which we'll be presenting just shortly. So once you kind of go through the overview of the solution, Daniel, then I'll hand it over to you so that you can share your screen and give everybody the opportunity to see what you accomplish.
Thank you, Blair. Hello, everyone. It's a pleasure to meet you. So just before we jump into the live demo, I would like to just outline the technical characteristics of the model that we have built for this demo. So the main challenge was to train the model to recognize 5 different human activities: brushing hair, brushing teeth, which are very similar, by the way, clapping, washing hands, and the 5th class is a random class, whatever else you might want to be doing, other than brushing hair, teeth, and clapping. And the challenge was to train the model on data, and then on data collected from 7 different people, and then to test it on the people that were not used for collecting the data, myself included. So we've used the data from 7 different people from all over the world. They have assembled their Nikola their own way. So this is how I assembled mine. So it's basically on top of the watch with the wire just running down to my PC. And all of them have assembled the Nikola their own way and collected 10 minutes of raw data, raw signal data, accelerometer, gyroscope, and linear accelerometer for each one of the 5 activities: brushing hair, brushing teeth, clapping, washing hands, and a random class. And we've used all that data and took advantage of our platform to train the model. And we've trained the model that can recognize human activities and generalize on people that were not used to training the data with 98.5% accuracy. And down here in the table, you can see the main model characteristics. So the overall solution footprint, including the model itself, the pre-processing and inference engine, is slightly under 5 kilobytes, which is very small. And by the way, if you look at the competing solutions, like in open source frameworks, which are at the heart of other AutoML frameworks, and just open source algorithms on their own, we've tried all those different tools, and the models that come out of those tools are from 20 to 100 kilobytes in size. And generally, their accuracy is only up to 95%. I think 95.5% was the highest that we were capable to deliver using TensorFlow. So this model is very small, and it provides generalization capability on new users with 98.5% accuracy. So without further ado, let me just demonstrate how this works in a live demo. So let me share my screen. All right, so hopefully now you can see the output of the model right now. As we speak, it is predicting a random class because I'm not doing any activities, and I might as well be just doing anything else. It would not false detect and predict that I'm brushing hair or brushing teeth or anything like that. So I've got my tools here, and let's do brushing hair. All right, right away you can see that, and by the way, I can do this in different directions: left to right, right to left, back to forward. And as you can see in brackets, it provides the probability of the class that it predicts right now. So we can see that the model is pretty confident in predicting that I'm brushing hair right now. Now let's try a very similar activity in terms of motion. So I'm going to brush my teeth. Okay, perfect. It has slightly lower confidence, but still it predicts with a 99, 98, 90% probability what I'm doing right now. Now, washing hands. And I'm actually doing this wrong because we have instructed the participant that collected the data that to do it like they do it in real life, that is standing up like next to a sink. And I should be standing up while I'm demonstrating this to you, but as you can see, this still is recognizing with pretty high accuracy that I'm washing my hands right now. And the last one is clapping. Well, this one is basically the easiest one with 100% probability. It recognizes all the clappings. And what is the most important for models like this, so they could run on always on devices, so they would not false detect when you're walking around or just going about your business, and only then, only when you are brushing hair or teeth or whatever other activity you train the model to recognize, only then it will recognize it. So I can be doing anything else, walking around, drinking tea, talking on a telephone, is going to predict a random class. And for the random class, we've also collected data that that the model was pointed to as the random class, because I mean this is a whole separate class. So that's really it for the demo. It's very quick, and I guess I'm going to hand it back over to Blair, and I'm going to keep this on. And in the Q&A section, in case you guys have any questions, I'll be happy to address them.
All right, thank you, Daniil. I'll take a moment just to reshare my screen once again. As I mentioned, one of the things that we really kind of wanted to do to begin today's session was, of course, to show everything in action, to give everybody the opportunity to see really a phenomenal solution, as Daniil has mentioned, that is less than 5 kilobytes in total footprint, which oftentimes you will find leveraging other well-known frameworks that you will probably have a model that is closer to 20 kilobytes or 100 kilobytes. So when it comes to, being active in the TinyML community, or being able to generate these solutions today, we're certainly happy to be able to have the opportunity to share with you guys what we're able to accomplish with our platform. Now, just to now maybe give you guys a little bit more insight and a little bit more information about who we are as an organization, I will take just a few minutes to kind of share with you guys not only who we are as an organization, but also provide some additional insight as to how we're able to accomplish some of the results that you guys have seen today. So one of the key solutions that we just mentioned is we're very active when it comes to human activity recognition. Daniil so far has been kind of, I would say, humble, but our solution, or the solution that you were able to see, you're actually able to either add many more additional classes, but also you have the ability to, if you have other functions when it comes to hand movements, you can certainly do that as well. Of course, we're not limited to the human activity recognition side of the house. So when it comes to audio, when it comes to predictive maintenance, et cetera, we're pretty active in this particular area as well. Now, one of the things, at least for myself, I had the opportunity to participate in Embedded World in Germany, as well as in the TinyML Summit that just recently occurred in San Francisco. And one of the key topics in both of those particular events is being able to really clearly show from an end-to-end solution perspective how you're able to accomplish a number of these different feats. And I want to take that moment to now to kind of give you guys some insight as to how we're able to do that technically. Now, one of the things that Daniil mentioned is that when it comes to our approach is different. We're not leveraging some of those well-known frameworks that you may be familiar with. This is a framework that we've developed in-house. We have our own algorithm that we've patented, but more importantly, when it comes to really driving the community forward, we wanted to also put together a solution that enabled everyone. Our mission for some time has always been, how do we make machine learning available for everyone, irrespective of where your maturity level may be from a technical perspective, irrespective as to where you may be from an organizational perspective in your journey. So Neuton is also a completely zero code TinyML platform. One of the things that Daniil will demonstrate later on throughout today's event is how you're able to repeat some of the things that you just saw him demonstrate without any coding along the way as it relates to building the model. Now, additionally, one of the things that we wanted to address our focus on is to be able to enable everyone to be able to implement our models irrespective of vendor, as well as if you have an 8-bit MCU, you have a 16-bit MCU, you have a 32-bit MCU. But also, I like to add an additional point here is, what about if you would like to embed that model directly onto the sensor? You have the ability to do that as well. So when we're talking about building models that are less than 5 kilobytes in size, now you can embed that model directly onto your sensor, further reducing the amount of power consumption in order to execute on your solution. And we're able to do everything that you just saw Daniil demonstrate, everything that I just discussed at the moment. We're able to do that in one iteration without performing some of those other techniques that you would probably have to do with other well-known vendors. So typically you're building a model, you build that model, then after that, you have to take some additional steps to then maybe reduce the size of the model so that you can embed it into your respective device. With Neuton, you don't have to do that at all. So in one iteration, we're going to produce that model that's extremely small and compact that you just witnessed, but you don't have to perform any of those additional techniques as well, where you typically are compromising accuracy along the way. Now, here is just kind of like the next slide to kind of highlight some of the things that I just kind of mentioned in an overview perspective. It is an algorithm that we've developed in-house, even though sometimes, patented, can be a bit of a boogeyman. All of the models that we produce, since we are device agnostic, are completely open. But one of the other more important things is that as we are achieving some of these accomplishments that you've just seen, is that we don't follow, let's say, the standard approach. We eliminate forego the need for any error back propagation. We don't apply or do anything as it relates to stochastic gradient descent. We grow all of our models neuron by neuron. So where typically you're starting out with a fully connected network and then taking steps moving forward, we take a different approach. We grow all of our models neuron by neuron, performing cross-validation along the way, just so that once we've now reached the model at the accuracy that you're targeting, we don't then have to perform any of those additional steps that I've just mentioned. Now, we do excel as it relates to sensor-based data and audio data, but of course, we're not limited to there. So if there's a couple of different things that I would like for you to take away, is that number one, we're empowering everyone, irrespective of your skill set. So if you're a seasoned, data scientist and you're looking to scale, you can leverage our platform. If you are new to building models and you're just beginning your journey, you can take advantage of our platform. And you can do that. We streamline everything without any coding along the way. Now, in the end, when you're looking to be involved in the TinyML community, or you're looking to embed models into any respective device, one of the key things that we all know, and I'm sure you guys know as well, is that energy or power, that's basically your currency. So the objective of being able to build a model, embed that model into your specific device so that you have the ability to produce a solution, improve its intelligence or functionality, but then you don't want to compromise your energy consumption along the way. And that's one of the key challenges that exists in today's market that we are addressing. And we're doing that, as we've shown you already to date, combining our platform as well as with some of the solutions from our partners, such as Arduino, as well as Bosch. Neuton allows for you to have the best of both worlds, and hopefully you're able to take that away with you at this particular point. So if you have some challenges that are out there where you have low power hardware, if you're looking to implement, in this particular case, if they're audio solutions, hand activity or human activity solutions, and if you would like It's one of the things that I added in the previous slide. If you would like to be able to have the ability to embed your models or increase that functionality directly onto your respective sensor or even your MCU, then certainly Neuton is the solution for you. So we're certainly enabling all of you guys to be able to bring that intelligence to any edge device, any low power, always on device. We're able to help you address some of your challenges. And as you can see today, we've partnered with Bosch as well as Arduino to bring you the solution that we're discussing at the moment. So we're combining both of those particular areas from a software as well as a hardware perspective to be able to demonstrate what we've shared with you guys so far at this moment. So what I would like to do now is I'd like to take a moment and I'll hand it over to Andrea, who will now share with you guys some of the cool things, some of the more innovative things that Arduino is doing today. So with that said, I will stop sharing and I will hand it over to Andrea.
Great, thanks, Blair. Thank you, and also Daniel for giving this demo. That was absolutely impressive. Now it's my time to share my slides. Okay. Now you should see my screen. No. Oops. Of course, just one moment.
Meanwhile, I just would like to say to all our participants, don't worry, we see your questions, okay? And we will try to answer all of them after we finish with the presentation. So be patient. We will read them and answer them, okay? Thank you so much.
Okay, great. So thanks for having me today. This is a great webinar. So before we saw the demo that was really amazing, I would just to give you some insight on the Nikola family. So Nikola family is basically a range of industrial grade sensor packed into tiny footprints. So we're talking about tiny ML, we're talking about tiny footprint, we're talking about tiny hardware. So what is the common values among all the Nikola family board is that there's a tiny form factor. It's really easy for configuring, have an instance setup and giving high level data. Due to this form factor, due to its capability, it's easy to create a wireless sensor network. So you can have a scenario where you have multiple boards connected to a central with intelligence on board, and then connected to a central piece of hardware that sends and collect and sends data. Then, of course, when it comes to the Nikola Sense.me, of course, we have also state-of-the-art and industrial-grade sensors. Then later on, ZG will go in deep. It's a low power and high-end machine learning, as you said. We have multiple examples on the usage of our boards into the tiny ML and AI space. Can host intelligence on the board. So while of course there's a model running, then of course you will have also our standard Arduino IDE language running on the board. When it comes to the connectivity, depending on the board, we have different solutions. We have Bluetooth communication, we have Wi-Fi communication, or Wi-Fi and Bluetooth communication, and of course it's compatible with our MKR and the Portenta form factor, and it has also an SLOF connector that it's basically an I2C connector that can manage local connectivity, wired connectivity. And due again to this combination of features, it's really fast to deploy these boards into project within existing infrastructure. So the Nikola Sense.me combines 4 state-of-the-art sensor from Bosch. It's able to detect rotation, acceleration, pressure, humidity, temperature, air quality, and CO2 levels. So there's a lot of stuff that you can do with this board. So that's why it's called Sense ME, where ME stands for motion and environment. It's when I told about the tiny form factor. When I say tiny, it's really small, because we are talking about 22 by 22 millimeters. So you can imagine that it's really a little stamp. But of course, it has a robust design that combines sensor fusion and AI capability on the edge. On a technical standpoint, I don't want to go in deep with the sensor, but generally speaking, the microcontroller, it's a Cortex M4. It has an I2C bus, serial ports, SPI, ADC they can use for your projects. It can be powered through USB, of course, through the pin header for external power, and it has also the capability of being powered through 3.7 LiPo battery, and it has an integrated battery charger. When it comes to the memory, you can see we have 512 kilobyte of flash, 64 kilobyte of RAM, and then we have 2 megabytes of SPI flash for storage, and 2 megabyte QSPI dedicated for a specific sensor. It's the BHI 260. I will just to give you an example of a real-world application where we saw the implementation of the NickleSense. In this case, it was a vibration analysis for predictive maintenance. The customer was curious, and he was to want to predict the drill bit life. So analyzing the vibration of this machinery, he was able, after some training, to determine which was the state of the drill bit in order to have a more improved customer experience and sending all the repairments equipment, all the spare parts when was the time and not before. So in this way, it was able to give a great and improved customer support to their customers. Now, last part, I would just give you some insight on our other products. And here's the time of giving some ideas around Opta. Opta, it's a micro PLC. We recently launched. It is available now in the market. It has industrial IT capabilities. Of course, can run models on it, so you can run inference within using the 8 inputs that has the digital or analog inputs, and then you can drive 4 relays as output. So this it's a real IoT micro PLC. Can be used for real-time control, monitoring, or predictive maintenance application. On the computational power, we are talking about a high-end solution because it has dual-core microcontroller, the same that we have in the Portenta H7. So it's a Cortex M7 plus a Cortex M4, giving you a full range of possibilities. And of course, we have all the available software, can be programmed and can be used with over-the-air firmware updates. It has secure element as per only every Arduino connected board. So give it a try. You will find all the information on our website. And then last but not the least, during Embedded World, so Blair was mentioning visiting Embedded World. So during Embedded World, we presented the new Portenta board, Portenta family board. It's a Portenta C33. It features a Cortex M33, so it's positioned in an efficient way between the Portenta M7 and the MKR boards. So it has a Cortex M33, it has Wi-Fi and Bluetooth on board, And of course, again, it's as a secure element to be a good partner for any IoT driven application. So again, you can perform over-the-air updates. You can use it with Arduino Cloud or with other clouds, of course. And again, it's one of our latest system on module that you can use for running AI on it. So if you want more information about the sports and all the other Pro products, visit us at arduino.cc/pro. And then I give the word back to Blair. Thank you.
All right, thanks, Andrea. I certainly appreciate all of the insights that you just provided. Next up that we will have will be ZG. And ZG will now take a moment to provide some insights that are available from Bosch, specifically on the sensor side. So ZG, if you are ready, I will hand it over to you. And just by way of update, and after ZG, then we will then go into our second demo. So ZG, are you able to hear me okay?
Yes. Can you guys hear me okay?
Yep. All right, perfect.
Great. Okay. So let me. Okay. All right. Can you see my screen well?
Yes, maybe if you can go into full screen, that might help, but I can see it perfectly well, but yeah, maybe full screen would be okay.
Okay. I think it is full screen or
Okay, all right.
somehow.
I can see it. I can see it. I can see it fine.
Okay. Sorry, it seemed like my screen sharing has been paused. I don't know why. Maybe let me stop it and resume it again. Sorry about that.
Okay, I can see
Okay.
it now in complete full screen now.
Great. Okay. Thanks for having me. So great speech from Andrea and a great demo from Daniel. So hello everyone. Thanks for joining us today. So I'm really honored to have the opportunity to speak to you on the topic of sensors and machine learning. And in this webinar, I'd like to share some insights that I hope will be useful for you. As you know, over the last decade, we have seen an explosion in the number of IoT devices, thanks to the rapid development in technologies of sensors, wireless, and machine learning. However, we know that there remain some challenges faced by both the developers and end users. For example, sending raw sensor data to the cloud for inference are causing latency issues and privacy concerns. And even for some IoT devices that are claiming to run the machine learning on the edge, the battery are still draining too quickly, making the machine learning, making the always-on applications impractical. This is why the on-sensor machine learning is becoming a very attractive approach, which could help address those issues and fuel the growth of IoT to the next level. So before we dive into the details, please allow me to give you a very brief intro from my background. My name is ZG, and or Zhenguang, or ZG for short, and I'm a sensor engineer from the business dev team of Bosch Sensortec. So I have been working with the company for a bit over 10 years, and thus I'm fortunate to see the major part of the growth trajectory of the company, which is, by the way, it's the market leader of MEMS sensors. And I've also been able to witness how our sensors have evolved with the market and the whole ecosystem over the years. And that's something I want to share with you in today's webinar. So in a nutshell, I have seen a few major trends. First, in general, the size of the sensors have shrunk, and quite dramatically for some sensors. For example, our first accelerometer launched in 2005 has a dimension of 3 millimeter by 3 millimeter, which is about 10 times the surface area of our latest sensor of the same sensor type. So the smaller sensor size matters because it offers larger flexibility, especially for the space constrained applications, such as hearable and wearable devices. The other clear trend is about power consumption. Our latest ultra-low power accelerometer consumes about 40 times, or even higher. Even larger scales of, lower current compared to the first accelerometer that we made. This is crucial because today many digital features that are integral part of our daily lives are always on, literally 24/7, powered by batteries, which are oftentimes very low in capacity. For example, earbuds, right, like AirPods, keep the accelerometers always on to detect user intentions, such as stopping the playback of music by simply moving the device out of the ears. So here it's worth mentioning that when we are talking about the power consumption, we need to look at the bigger picture. So of course, saving a few hundreds of microamps of current on the sensor alone does not help much if the power-hungry processor must keep awake to process the sensor data. So over the years, a lot of sensor features and new system architecture have been introduced, such as a deeper FIFO memory on the sensor, and more importantly, localized sensor processing have been able to not only reducing the power on the sensor, but also the system power. So sensor performance, the other thing is that sensor performance is also constantly improving with better noise, accuracy, reliability, and stabilities. For example, the sensors changes of offset at different temperatures are getting lower, even over a long time. This is helpful for problems such as domain skew in the machine learning community. So sensors are also getting smarter. For example, sensors in the early days are rather primitive, equipped with some simple interrupts, if existing at all, and a serial interface like SWRC to spit it, roll it out. And the sensor today could recognize user-defined patterns all by itself with very low power expenditure. So finally, we also have new sensors that can measure different physical properties added to our portfolio every new year. For example, our gas sensors that can, sense the different kinds of gases, VOC gases in the environment. So today, our sensor product portfolio consists of several segments, including the standard motion sensors, environmental sensors, and smart sensor systems, which are the focus of our discussion today. So there's a long list of part numbers in our portfolio, and that's why we don't list them in the diagram. So the rule of thumb is that as you move up or to the right, the sensors will pack more sensing capabilities, features, or intelligence. Hopefully this gives you a better overview of our product portfolio and a better way. The naming convention of our sensors are pretty straightforward. It always, not always, but almost always starts with a B, and then followed by M, standing for MEMS, and then you have another letter that basically dissipates the kind of a sensing capability of the sensors. So in a typical edge AI system today, you have some microprocessor that runs machine learning algorithms based on the data from some simpler sensors, such as our BMI. And some of those sensors are working just fine. So the question is, why do we bother having the smart sensors or smart sensor systems in the first place? So again, let me share some background based on my experience, right? So a few years ago, after the first wave of excitement and success in the mobile market, the Android OS introduced some always-on features such as step counter, that users could track their steps automatically. It might sound ridiculous today, but some early OEM implementations of the feature were run on the SoC directly. And it's not surprising that it did not provide the best user experience when the user had to charge the phone more often. So our study showed that by simply porting the same machine learning-based algorithm to a discrete sensor coprocessor, such as a Cortex M4, cuts the power down by a factor of 10 times. And this 10 times progression scheme goes on with our smart sensors, smart sensor systems, and even smart sensors. And by pushing the processing closer to the sensors, the benefits don't stop here, right? So, there's no more latency or reliability issues involved with sending the data to the cloud. And same goes for the privacy concerns. And secondly, even with many edge AI applications, we don't require raw data to be sent to the cloud. The main processor may have a limited bandwidth processing sensor data, especially when a high data rate is required, risking data loss, which could break the machine learning model, right? For example, wireless SoCs need to follow the precise and sometimes stringent timing requirements to keep the BIU stack afloat. And so it may need to drop sensor data when timing conflicts arise. By pushing the machine learning closer to the sensors, the risk of data compromise is eliminated, right? And so running the machine learning on the sensor is not only efficient in power, but also in economy. So the BOM of using a single smart sensor is usually lower than using discrete components. In addition, the PCB of the size could also be much more compact. And the Nikola Sense is a good example. For example, I have a Nikola Sense Me with me. And so the Nikola Sense Me is a good example by using the smart sensor BHI 260. So without further ado, let's take a quick look at how the smart sensor looks like from the high level. Our smart sensor system hardware consists mainly of the same MEMS and ASICs that you could find in our standard MUs. And then in addition, we have an efficient 32-bit ARC EM4 and microcontroller all integrated in the same package. On the software side, we have some pre-built application-specific solutions, oftentimes based on machine learning. So including standard features such as non-DOF sensor fusion for rotation tracking, head orientation software for our for 3D audio applications, pedestrian directioning, and some pro features such as swim analytics, pedestrian directing, and more. So for our audience of the webinar, what is most important to take away is that the BHI smart systems are programmable. So the software platform comes with all of the components such as, SDKs, toolchains, drivers, and programming manuals to allow new algorithms to be developed and deployed on the smart sensor platform. So please feel free to check out our website for more details. All right, that's all for my presentation. Thank you for your attention.
Thank you so much, ZG. It was extremely informative, and I think you raised a couple of key points that I will just touch on. One of the key things that you mentioned was, having the ability to not always have your MCU waking up every time you run inference, as an example. So one of the key things that when it comes to let's say for us, when it comes to having the ability or having a model size to be able to embed that model directly into the sensor reduces, your overall power consumption, which is essential. I always like to say that the power that you have on any always-on device is your currency. So we certainly love the partnership that we have with you guys, have the ability to, embed our models directly into a sensor. And the same thing, there are some additional key points that Andrea mentioned as well that I think are essential as it relates to, having an ability, irrespective as to where you may be in your journey, whether you're a seasoned data scientist. I encourage everyone to think about Neuton. If you're new, you're just now beginning your adventure, certainly Neuton can enable and empower you as well. And as technology continues to advance and the form factors and the footprints become smaller, certainly Neuton can enable you guys along the way. But I like to now kind of get to what I think is kind of like the meat and potatoes of everything. We had the opportunity to show and demo everything in action at the beginning of today's event with Daniil, when he did an exceptional job showing our hand activity recognition model in action. And then from there, we kind of gave you a little bit of a background as it relates to Neuton. Andrea did an exceptional job highlighting the capabilities from Arduino, and ZG, you just continued that trend and highlighting what you guys are doing from a Bosch perspective. And I like to say that now we're putting all of the pieces together, and we want to share with you guys how you guys can accomplish everything that you've seen today. So it's one thing to say it, and it's another thing to actually be able to do it and then demonstrate it. So with that said, I'd like to hand it over to Daniil. Daniil will now give you guys an overview as to the simple steps that you would need to take in order to repeat what you guys have already seen today. So with that demo that started today's session off, I'd like to hand it over to Daniil, and then now Daniil will demonstrate and show how you guys can accomplish this as well. So with that said, I'll hand it over to Daniil.
Thank you, Blair. So I'm sharing my screen. Can you see it?
Yes.
Okay, so we have posted on Hackster a very detailed manual on how to, first of all, repeat the experiment that I've shown to you, and also how to train the model on your own data, how to collect the data, how to use NickleSense ME, Arduino SDK to do everything together with the Neuton platform, so you can train the model to recognize your activities, whatever you have in mind. And basically, of course, we'll share the link to this story, and I'm gonna skip the intro because you already know what's going on. I've already demonstrated to you the solution, because I mean the intro describes basically everything that I've shown to you and how it works. And just before we dive into the manual, here there is also a link to our GitHub repo, which just in case you want to try this model on your own device, and the one that I've demonstrated to you, and just make sure that it generalizes on new users with the same accuracy. We have precompiled an Arduino sketch, and it's here in the repository. Hold on, let me show this to you. Yeah, it's very easy. There is a manual, so you just basically you download the model from here. It's a zip archive, and everything is described here with basically like 7 screenshots on how you can embed this into your NICLA Sense ME and start inferencing. And you can just brush your teeth the way you do it, or brush your hair, and see how the model will recognize these activities. And you'll be sure that your data was not used for training this model. So you can start with that, just in case you don't want to go over the hustle of collecting all the data and training the model. But if you have something in mind, some of your specific activities that you want to train the model to recognize using our technology and NICLA Sense ME, so here's the manual for that. And let me just quickly go over the steps, and then I'll show you the platform and how it works. So basically everything, and it goes in the context of today's demo, so these classes can be anything that you wish. So it starts, the first 7 steps are regarding installing the Arduino software on your machine and updating it and installing all the necessary libraries. And it's basically a step-by-step with screenshots. So once you do these 7 steps, you'll have your software on your local machine configured. So you could use it for collecting the data, for inferencing the model, and so forth. So after you have configured the software on your machine, up until step 7, now you have to configure the NICLA to collect the data. Now, of course, you can go inside the Arduino SDK yourself and then start writing some code to collect the data coming from NICLA to the serial port, but we've made your life a bit easier. So again, in the same repository, in this same model folder, in this same archive, there is a second project which enables you to collect the data with NICLA without having to write any code. You just install it in our manual here. We basically tell you that you download the model and Arduino Newton zip, and this is how you install it into the Arduino board. And after that, you can start collecting the data. Accelerometer, X, Y, and Z, gyroscope, linear accelerometer, X, Y, and Z, and gyroscope. So after you have configured your NICLA to collect the data, now you have to assemble it. So hopefully you can see me. So the way I did it, I just bought the cheapest watch on Amazon and glued a little wooden pad on top, and then I just attached my NICLA with a duct tape. So you can do this on your own without any problems. Just make sure that it points the right direction. There are axes here that are drawn, but the rule of thumb is just that the cable has to be facing your elbow. So that's it. You attach it on a NICLA or on a watch. Now you have all the 3 pillars configured. You have your software on your machine. You have configured the NICLA. You flushed it with firmware that is going to collect the data, and you have your device on your hand. So the next thing is, and again, the manual in all the details explains to you how to do this, and you have all the checkpoints here. So after all of this is done, you basically start collecting data. And you collect for every activity, you collect a separate data set. For example, you start with brushing hair, as you can see here on the screenshot. So you start the data collection process, and you start brushing your hair for like 5 or 10 minutes, for instance. And then you stop this process, you save the CSV, and then after a few moments, you can start collecting a different activity. And after that, you'll have a few data sets. In this case, in this example, there are clapping, brushing teeth, washing hands, brushing hair, and there was also a random classes, not on this screenshot. After you have all these 4, 5, 10, 20 data sets collected for your activities, you just concatenate them together sequentially. And this is your data set, which you can now use to train the model using the Newton platform. Now, the next section is geared towards, with screenshots and all the details, showing to you how you can take advantage of the Newton platform, and it's free. You can just go ahead and register and upload your data and train the model. And instead of going through this manual, let me just, it will take 5 minutes. I'll show you how this is done on the platform. So after you have registered, you'll see this workspace here. This is the main workspace. Mine has a lot of models. Yours will have no models. So let me just quickly show you the workspace. You can launch as many experiments with different settings as you like, because for every one of them, Google Cloud will provide a dedicated virtual machine and they all run simultaneously. So in your case, after you register, you have nothing here. All you have to do is add new solution. So the first choice you have to make here is what type of data are you using? And we are solving 3 different problems. So audio data, which is basically you can upload WAV files here and train the model to recognize different activities like wake words or some different events like breaking glass and things like that. Sensor data and tabular data. So tabular data is basically a full-blown AutoML. If you want to predict, I don't know, sales or customer churn, you have a data set with missing values, outliers, and dates and things like that. So this is a full-blown automated AutoML. You can do that. But since today our business is TinyML, so sensor data it is, and let's give it a name. All right. And the solution is created. Now here you can see the 3 steps. There are only 3 steps. So very easy. Upload your data on the first step, configure training and run training here in the training step, and in the predictions tab, you can access the model quality and download your model for embedding. Now, basically this starts with uploading a data set. Just let me grab a data set. Quickly, you can drag and drop. And so this is the data set that you have collected with your Nikola according to the manual that we have just looked at. So, all right. Now, while the data set is being uploaded, the platform is checking for the data validity. So for the TinyML use cases, you cannot have text data in your variables or missing values. So yeah, this is basically what it does. After everything is checked, if everything is okay, it proceeds to the next step. And just let me show you what I've uploaded. We have a viewer here. It's the data set for this particular use case, and we're using accelerometer X, Y, and Z, and gyroscope X, Y, and Z. And this is the label column. So this corresponds to label 4, and in my case, it's brushing hair. And every one of these records is just 1/100th of a second of data collection, because we've been collecting our data with the 100 Hertz frequency. So this is the data set, and you can click OK. And one last thing you want to do here is to select the target variable. So these are our columns, and the target variable is label in this case. And yeah, one more thing. So just in case you have a holdout validation set, and if you want to validate your model after it's trained on a holdout data set, you can upload it here. And the process is just the same. You just drag and drop. And that's it. The platform will run the final validation and display in the interface the metrics for you obtained from predicting and validating on this holdout data set. In another case, it's going to run cross-validation on the trained data, and we're not going to use a holdout set. In this example, we'll just do cross-validation. The platform will do it all on its own. So only one step here, target variable, and click next. So now we are on the training tab, and this is where you set up training parameters. So it's really not a lot, but all of them are essential. So let's go top to bottom. So this is a multi-class classification because we have more than 2 classes. We have 5 classes. And we know that our input data type is integer 16, all right? And now, since this is a digital signal that we are working with, like accelerometer and gyroscope data, and there is actually a tooltip here, we want to enable digital signal pre-processing. So let's enable that. And the main parameter here is the window size. So what is going to be the window of data that will be used for extracting features out of a digital signal? Because from one record, measured at 100th of a second, you cannot understand what the person is doing. You need to collect a second or half a second to figure out whether they are walking or brushing hair, brushing teeth, whatever activity is happening. So a window of samples has to be used to extract features out of. For my model, I've been using a window of 200. That is equivalent to 2 seconds of data. And you can also use a sliding shift. So basically, let's say 100 here. So what it does is going to, for the first sample, is going to take 100 records, 200 records, and extract a digital signal out of them, then slide 100 records down, take another window of 200. So it will basically overlap, and this will effectively increase your training data by twofold. And this is very good if you have a smaller data set, and you can even go much more aggressive and say 20 is going to be a sliding shift. That means your training data set, whatever the size is going to, after data preprocessing, be 10 times larger. And we have a separate setting, which you can also separately set up for inference. So for inference, say you want a sliding shift of 100. It will not affect training, but since the platform provides a model and all the necessary code to be embedded on the MCU without you having to code anything, you can define this here. And the archive with the model is going to contain this logic, and it will run inference with an overlapping window of 100. Okay, so by default, the platform is configured to, well, based on our experience, to extract the best features possible and not very heavy features in terms of inference time. But you have the control over each one of them. So here are your features: axes, accelerometer X, Y, and Z, and gyroscope X, Y, and Z. And you could go into any one of them by clicking edit. And basically, these are the features that we extract. Let's open them. So by default, it will extract out of a window of 200, which we have defined for accelerometer X, mean, max, min, root mean squared, and so forth. And you can enable or disable any one of them and run your experiments with any set of features. Also, we have amplitude features and even some frequency-based features for some heavy lifting. And of course, they are also used for audio data preprocessing. And you can do this individually for any one of the axes. Let's not change anything. We'll go on all defaults. We also have some feature selection methods here if you wish to experiment with. And there are tooltips that explain how all of them are used. And last but not least is the bit depth of your MCU. As Blair has mentioned, we are MCU agnostic, and you can basically select you don't even need to indicate the model of the MCU you want to embed this into. You just know that this is say the smallest one possible 8-bit architecture, and it does not have float data type support. So these are your settings. You can enable or disable them. And you can also, you have some options to stop the training, like you don't want, for instance, more than 1,000 weights. So this is your setting. Or you want the training duration to be 1 hour, or you want to reach 90.9 accuracy, and that's it. So you're free to do any of that. But we're not going to do none of that. Let's just start training. And basically, after you've done that, the platform will handle the rest. Everything will happen automatically. It will do all the windowing, data preprocessing, model training, and then packaging all of that into some C scripts that you can then download with your configured and trained model. So yeah, we can message you when this is done. And basically here in real time, you'll see all the relevant metrics based on cross-validation after each epoch of neural network training. And here you can see the same values graphically just on this plot. And right now the virtual machine is being created, and let's just not waste time. I'll open the identical trained model and I'll just show you the results. Give it a second. Okay, this one right here. Just to compare, so right now the status here is virtual machine is being created. It is at 3%, and this is our progress line. This one is finished, training completed 100%, and it took 1 hour and 43 minutes. It has reached accuracy of 0.999, which is very accurate. And basically, after this is done, it will automatically redirect you to the predictions tab. And here you can look at the rest of the metrics relevant to the or measured on doing cross-validation. So these are all the relevant for this type of problem metrics values. And this is, well, this blue line is not an outline, it's really a plot. So if your metric were to fall behind on some of the functions, you would have seen it here on the plot. But in this case, we can see it's nearly perfect accuracy on cross-validation. And actually, this makes a lot of sense because at inference, we have measured on about 15 different people, accuracy of 0.98.5. And it's a very slight decrease from the training cross-validation metrics. And also, and there is also the confusion matrix, which you can have a look at. Also, during training, on the training tab, you can dynamically see what is the current model footprint in terms of flash and RAM. And after training, this is the final model footprint. And this is not an estimation. We compile them for Cortex M4, and this is the actual model footprint, 3.9 kilobytes of flash. And whereas the model is 1.4, the inference engine is 1, and 1.4 is the pre-processing. And the same goes for RAM. And you can look at the footprint measured for Cortex M0. So after this is done, you can just download the model, and the archive goes straight to your downloads folder, and you can then just go ahead and embed it into the MCU. All the data pre-processing is going to be configured, all the windowing, all the sliding shifts, the model inferencing, and your predictions provision. And if we go back to our manual here, well, basically it's going to show you everything that I've just shown to you with screenshots. And yeah, this is the contents of the archive, and you can then just go ahead and embed this into any MCU, because this is MCU agnostic. This is just C code, which any MCU can execute. And we really encourage you to use your own data and see what the platform can do for you. If you have a Arduino Nicholas Sense NE, you can go ahead and test the model that I've shown to you without having to collect any data, and just in 20 minutes you'll be able to figure out what does this model actually, what is the actual accuracy of the model on your activities. So yeah, that's it. If you guys, and I know there are lots of questions. I don't know if we go to Q&A right now, or do we have anything else to discuss?
I think at this time, I'll probably hand it over to Julia, and maybe she'll guide us.
No, we have a lot of questions to you guys still. So we start to answer them, but I think this is the, yeah, before we start the Q&A session, actually, Blair, thank you to remind me. Yeah, just make it bigger, and I will explain a little bit about our giveaway. So we decided to make it super simple this time. So everyone who make at least one question in Q&A session, and now we have already more than 13 questions, I think. So all of you guys already could participate, sorry, in the giveaway. And the second condition that we ask you to register to our free plan on Neuton.AI platform. By the way, I would like to repeat that you can use our platform for free. We don't charge for using our platform, so please take advantage. Not only because of the giveaway, but also to make your own projects, to repeat the experiment that we just share, to make your models. Please welcome, register on our platform. Here you have the link, but just go to our webpage and start for free. So we will give the time during the webinar, during this evening. For someone is morning now, and we will announce the winner tomorrow. Tomorrow at evening set time in our LinkedIn page and in our Slack channel. I think I already shared with you guys a link to join our Slack. If you miss it, I will repeat it again. Also, you can see it here. You can make a photo. Anyway, we will share the records afterwards. So please be free to join us. We will be very happy to see there all of you guys, and be active now in Q&A session. I wish you good luck and giveaway. And Blair, I think this is the time to start answer questions that we already have. Yeah, I see Andrea is already typing some answers. I don't know how we are going to do this, Blair.
Okay.
Maybe some of them you can read and we can answer them live, and some of them we can answer in the chat. Mhm.
Julia, I propose that we just go one by one. I've read all of them, and great questions, by the way. And
Yeah,
we'll
sure.
do our best to answer all of them. Okay, so yeah, so the first one is, would you mind trying putting a teaspoon into your mouth and moving it, or a pen, just to see what recognize? Yeah, I tried that. I've disabled my camera and I use my pencil, and it does recognize brushing teeth. But I mean, that's what I'm doing, right? Whether this is, you can take the other end of the toothbrush and do the same, and you're going to still be brushing teeth. So not naturally, it's going to recognize brushing teeth because this is the actual activity that I'm doing. If I were to drink tea or speak on a telephone, it would not see brushing teeth. But if you're doing something that actually is that, but without using the proper tool, it will recognize it. Okay, so the next question is, how repetitive does the motion need to be for the application to recognize it reliably? Well, I have to say that it's not the actual nature of the motion, but the number of samples, training samples you provide for that motion. You can be idle and sleeping, and this will be the class the model will recognize. Or you can be, there's going to be a question there, and I guess I'm going to answer this right now as well. There is a very interesting use case to predict fall detection. So basically, it's not a repetitive motion. The person just falls down and waves their hands, and this is just one small activity, but it's very differentiating from anything else. And this will be if you have enough training samples to show where the person is not falling, then naturally you have the majority of those, maybe 99% of them, just walking around doing something, and some information or some samples that will show that this action means falling down, and is going to be appropriate label. There's giving enough training samples to teach the model to recognize those, and then the model will recognize them, and it will be not a repetitive motion, but you have enough training samples to recognize that somewhere in a time frame there's going to be a very distinctive motion of waving hands, for instance. All right, so okay, the next one, can we use Newton?
Daniel, just maybe you can share your screen so everyone can see the questions, and it will be.
Yeah, sure. Just a second. Give me a second, please.
If you open Q&A session, maybe.
Or I can open it, and then you can just step through.
Yeah.
But
Yeah,
let me reshare. I'll do it just to make it maybe a little bit easier.
Yeah, I'll go for the next
What
one.
about now? Can you see?
Yeah.
I don't know if it's sharing the Q&A or not.
Yeah.
No, it's not.
No, it's not.
Okay, so I'll try. Go ahead.
Okay, good.
If you stop sharing, then I can share. All right, you should be able to see my whole screen right now. So yeah, can you see it now? So all right, can we use Newton TinyML for object detection?
Anil, I think we don't have
It
this.
doesn't show the Q&A in the share.
All right.
Just
Okay.
continue.
Yeah, all right. So no, Newton cannot do object detection. We don't do images, and yeah, this is out of the scope for now. And basically, this covers a few questions we have there on the list. Okay. So the next one is to rephrase the question: is it possible for the system to recognize a single motion that is only executed once? Yeah, I think we've answered that already. It can, once you provide enough training data to show those single motions and a label next to it. All right. So how do unsupervised learning algorithms like autoencoders work in training neural networks? And we don't do unsupervised as well, only supervised neural networks for regression, binary classification, and multi-class classification. But we cover lots of different tasks, like working with audio data, working with sensor data, and a very comprehensive AutoML platform to run any AutoML project, like, again, predicting sales. Okay, can you explain how adversarial attacks can be used to exploit weaknesses in neural networks? Well, that's a big subject. It's really a scientific study, you know, like There were examples like on Tesla self-driving cars, somebody would stick like yellow pieces of duct tape on the road, and the car would not recognize that. It would think that it has to deviate from the route. Yeah, this is a big problem, but I think it's a different domain. For sensor data, adversarial attacks, I don't think this is really a big deal, because for instance, like in our example right here, I'm wearing the device on my arm. And the only adversarial attack I can throw at the model is me just going crazy. I mean, that's a very unlikely situation and unlikely use case for this type of application. Okay, can you build an image-based model? Okay, we've answered that already. Is it possible to collect the training data through Bluetooth in order to avoid being threaded to the computer? Yes, of course you can do that. You just have to set up a BLE connection, but the one thing you have to keep in mind that your sampling, your frequency has to be low enough to be able to just be transmitted through Bluetooth bandwidth. So some very big, very high frequency of data collection is not compatible with Bluetooth. Okay, so we've got that. How accurate and reliable are the readings provided in nucleus family sensor, and what factors can affect the sensor's performance? Well, I guess this is a question to Andrea or ZJ. So how accurate and reliable are readings provided by the nucleus family sensors? Yeah, so once the gentleman will get online, we'll get back to this question. So
I think ZJ is here. Yeah.
Yeah, I'm here, but sorry, I couldn't see the exact question that
I can repeat it
was.
for you. So how accurate and reliable are the readings provided by the nucleus family sensor, and what factors can affect sensor performance?
Okay, yes. So without getting too much into the details, I think we have the data sheet, right? With all of the specs regarding the sensor performance, such as accuracy, noise, TCO, things like that on the website. But if you cannot find the information, feel free to reach out to me. I have posted my email in the chat. I can do that again. Yeah, feel free to reach out to me on those questions.
Okay, thank you, ZG. Okay, we've got that answered. How does nucleus family sensor differentiate between different types of motion, such as human movement versus pet movement? Well, this is not really a question for the sensor, but for the model that recognizes these activities. And I presume that human motions and pet motions are very different in their nature, and I don't think it should be a problem to recognize what's happening right now. So if you've been training your model on a dog, strapped to its chest where the dog is sleeping or running or sitting, and you have a correctly labeled data, it will accurately recognize that. And I bet if you try to replicate this by putting the model on your chest and try to run like a dog, it will not recognize. So yeah, that's just a matter of training data collection. Okay, so can you clarify whether your platform is able to, okay, it's gone. Are the customizable models available? The platform provides a very large combination of number of unique combinations of settings you can adjust for training your model. Just now, we've trained the model on all defaults. And you can run many different experiments by enabling and disabling different types of features for different axes. You can change the window size. You can change the sliding window size. You can select the feature selection methods. There are 4 in there. And basically, you can use different types of metrics to select the best model. So there are lots of different examples. And of course, you can use different features. Like you want to, for instance, use accelerometer and gyroscope, or maybe a linear accelerometer and magnetometer. So everything is up to you. Only in this case, you don't have to code. You just use your mouse to select the appropriate options, and that's it. Okay, so I've been using another ML framework based on TensorFlow Lite, also no code. I will certainly have to test your benchmark on model size and efficiency. A relevant R of opportunity of the other framework is non-enterprise customer support. Okay, I've read this. So you don't like the customer support of the other solution that that they provide for a free option. Our customer support is 24/7, and for any customer, regardless of the fact whether they are an enterprise or a private customer with a free plan, it's the same procedure. So the difference, or the only difference between the enterprise plan and a free plan is that within the enterprise, there is other channels of communication, you know, maybe over the phone. But for all the people that reach out through the platform, there is no deviation. They are enterprise customers or free customers. You'll get your reply. In most cases, you'll get your reply in a few hours, maybe even instantly sometimes, because there are people there all the time that are monitoring and answering those questions. But in worst case scenario, 1 business day. Okay, how does Bosch?
So, Daniil, I think ZG is maybe answering some of these questions. At least I can see him typing. So maybe I'll kind of just quickly go through and maybe identify ones that we should do live. Also, just kind of maybe keeping track of time.
Questions here.
Yes, I saw some.
Hey, sorry, I didn't realize when Julia was asking the question, I was on mute. Okay. Anyways, so what I said was that for the question regarding, you know, the reliability and accuracy of the sensor products. So what I can say is that our sensors will go through rigorous testing and the qualifications before they are mass produced and delivered to the market. So so the parameters that you see in the datasheet could be you know, could be relied on. So that's pretty much what I can say. There are many processes and standards that we confirm to. For example, you know, RoHS and also the, you know, standard regarding temperature and humidity cycling of the product under different conditions. Anyhow, so feel free to reach out to me on, you know, specific questions on the sensors, and feel free to reach out to me with the email that I provide in the chat box.
Thank you. Blair, there is this one small question. It's very tiny, but I think it's to the point. I want to elaborate on this. So why the total footprint is so small? We did not mention a lot or describe how the Newton neural network framework is created. So just to compare, a traditional neural network, any neural network, TensorFlow, PyTorch, or anything, will have a predefined neural network architecture. You will have to define it, whether through network architecture search or manually, that is going to have like 3 or 10 layers with 20 neurons in each. And even before you start training, you already know how many weights you are going to have. You can just multiply the layers and inputs and understand what is going to be the footprint. And you can also estimate after you compress it with TensorFlow Lite divided by 4, and this is going to be a footprint. And this is what you have to work with. You don't even know yet how accurate this is going to be, but you already have restrictions. And within this architecture of all the nodes that are in place, whether they are necessary or not, they will all occupy space. Some of the nodes of the neural net of the traditional neural network may provide much less value than the others. Their weight, just nothing would have happened if this weight was missing, but it will not be missing because this is the structure of the neural network. It's predefined and it's going to reflect on the model footprint. Newton doesn't work that way. That's why it's patented. So there is no predefined architecture. None of us, when we start training the model, know what is going to be the final output, neural network architecture. It will start from a single neuron, and it will connect this neuron to some inputs, not all the inputs. Then after having trained those weights of those connections through extensive cross-validation, up to 10-fold in some cases, it will connect another neuron, which may be then connected to the first neuron, or maybe not, and may be connected to some other inputs. And it will keep adding them one by one through the cross-validation process, where it makes sure that every one of them, because all of them are trained separately, will provide the maximum possible input into the model prediction. And once it understands that through cross-validation that it starts to overfit, it will stop adding neurons. That way, what we call, it will create a swarm of sparsely connected neurons. For this model, for instance, if you've seen in the table, there is only 136 neurons. Try doing that with TensorFlow. You'll have thousands of weights in there, just to say the least. So that's the in principle difference between other frameworks, regardless of the platform, because neural networks are all the same. And that's why we create such small models out of the box. You don't have to compress anything. There is no pruning. There are no redundant nodes in the network. All of them provide perfect sense for predicting the outcome. I hope I answered that. So Blair, any specific questions you want to target?
No, we can keep going. I was just referring to really kind of the ZG was typing. So,
Okay.
So we can go to the next one. Can I port my own neural network model?
Well, no, you can use the platform to train the model for you automatically, but your own neural network, there is no like a conversion tool from your neural network into ours, because they are in principle very different. So can provide some specific information on the architecture. Okay, I think I just did that. All right. So what are some potential future developments and enhancements that Neuton Labs is exploring for this technology? Well, basically, we want to adapt our technology to the widest possible range of use cases. We've just recently expanded into the audio space. We, of course, are looking at the image classification, but we're not quite there yet. So basically, the further developments will go in line of optimizing the digital signal pre-processing suite, because, I mean, regardless of the final network or the model, garbage in, garbage out. So in order to train the model to recognize those classes, you need to extract features out of your data. And that is done within pre-processing. I've shown to you that we have 3 different blocks of statistical, amplitude, and frequency-based features. We keep adding new ones, and for different types of problems and different types of sensors, some different other features may make sense and help to build more accurate models. But within the TinyML scope, we're going to be situated around that. So how Neuton is deployable on a variety of devices? Well, it's C code. You can deploy it on any device. It's agnostic. So just to be sure, you only use accelerometer and gyro, no cameras. I guess this is referring to this use case. Yeah, the only accelerometer and gyro, and you're more than welcome to download the model on your NICLA and do this again on your own with no video. Yes, only accelerometer and gyro. So what metrics are used to determine the efficiency of these tools? Well,
one second. Just to add to that question. So I just want to clarify. And it says you only recognize the 4 activities through that and no image data. But just to add that we're not limited to that. So, we have models that have more than the classes that were just mentioned right at the moment, but we don't use any camera data. So I just wanted to just reiterate that we're not limited to the number of classes that we demonstrated today.
Yeah, there is a question in this regard. There is, I believe, somebody said 12 classes in their use case. There's no problem. Of course, if you have 120 classes, it will be a hard time for the model to distinguish between them. But 12 is no problem. We train the model for much more than that, up to 50 classes and up to 100 classes. But the only factor that will affect the model accuracy, regardless of the number of classes, is the quality of data. So if you have different activities, you should have quality data and labeled data to represent those activities. And yeah, that's it. So can I get the same project with TensorFlow Lite, please? Well, you can certainly try and then just look at the outcome. First, well, what is going to be different? First of all, you're going to have to not only know how to code in Python or maybe R, whatever language of choice. You also have to be a statistician, mathematician, data scientist, an embedded engineer to arrive at the point when you can have an archive that you can download from our platform and to embed this into your MCU. So, and confidently, I can say that the model is going to be much larger. Okay, if it's 20 or 40 kilobytes, it will fit on a Nicholas Sense ME. And it might have a similar accuracy, but it will drain your battery. It's going to be very slow inference time, and you will spend a week of your time at least to be able to do that. Okay, how do you avoid overfitting? Well, as I mentioned, cross-validation. So, and that is the mechanism that primary mechanism to avoid overfitting. It will stop training just at the point when the cross-validation metrics start to decay. So I'm curious to know when the integration of Nicholas Sense ME and Bosch AI Studio will be available since, okay, so I guess this is a question to ZG or Andrea. I will.
Yes, so I believe I provided answer to that question. Okay, so anyways, so the AI Studio is a tool suite that we provided for gas classification with our BME 688. And so right now our team are developing the support for the Nicholas Sense Me. And so as far as I know, the development work is almost done, and we just need to do more testing and a review before it could be published to the external world. Hopefully that answers your question.
Okay, thank you, CG. So let's proceed. So, is there any labs? I don't know what you mean. If you could please elaborate with a little more context. So I'm gonna skip this one for now.
Yeah, there are no labs, but because we make our platform available for free, so you don't need to necessarily, let's say, use a lab. You just go to login.neuton.ai and sign up and begin to access the platform.
Mm-hmm. Where can we find the models? So the model that I've just demonstrated to you, I think Julia has already sent the link to our repo. You can download and embed. There is a manual. All the other models you can train on your own data, taking advantage of the platform. And I mean, there are so many different sensors and different activities, so it's impossible to train all the combinations of models and have them in Model Zoo somewhere. So just go on the platform, collect your data and train your model, and you can download it and then embed it. Can I train a fault detection model? Okay, we discussed that already. Of course you can, and we have a very good paper on IEEE regarding this use case. All right, can we collect data from an accelerometer ADXL335 sensor? I presume you can. I'm a data scientist, not an embedded engineer. I cannot confidently give you an answer to this question. But if this sensor has an accelerometer and this data can be collected through a serial port of a computer, of course you can. And the platform doesn't care how you collected the data. It will use that data to train the model. And if you can embed this model into your MCU or sensor, which we also do, you can do this with our platform. Okay, how many activity detection features can be classified per application? Presume you mean how many classes can there be? As I mentioned, we've tried many different use cases, up to 100 classes. Of course, it depends on the quality of data. So yeah, are libraries free to use? Yes, they are, as the platform is. Does the same accuracy be achieved with wireless sensors connected to the controller? It doesn't matter how the data is transmitted, as long as it comes uninterruptedly at inference, and this same data, the same frequency has been used for training. It doesn't matter if you collect it through a wire or wireless, the model will at inference predict on that data. So the accuracy will be identical to the accuracy which you have achieved in training. Okay,
can I ask you just to have a small break, because we have here Andrea, and we're already out of time. He needs to skip, but we cannot to leave him go right like this, of course. First of all, we would like to thank you very much, Andrea. Maybe you can say something to everyone before you leave, because we very appreciate you were with us. We very appreciate your amazing, insightful speech. Maybe you can say also a few words to audience.
Oh yeah, thanks. Thanks a lot. I try to address all the questions, by the way, really interesting. We get a lot of questions, so Daniel is doing a great job to go through all because absolutely good. But yeah, again, it's a really great platform. So I invite you all to try it because it's really great. And you saw here today that also the footprint, that it's really important. I saw some questions regarding, the footprint, the capabilities of, the entire model. And I think that today we've shown that Newton is a great platform, and the footprint was really good. If you think about all the things that were, modeled and trained, and so I invite you all the guests to try it out, because it's a really great platform. And yeah, so anything I was not able to address, please write us. And yeah, of course, all through our friends at Newton, and I will try to address all of them. So thanks a lot for having me today again, and see you next time.
All right, thank you so much.
Thank you, Andrea. And please also come to webinar that Andrea will host, I think next week. I saw some announcement. And yeah, we will try maybe to accumulate the most interesting questions to you, Andrea, and send it to you anyway. We are here for you for your next projects. Be free to address your questions and ask us. And thank you again, Andrea. We will be very happy to see you again. Maybe to Italy.
Okay, great. Thanks a lot. Bye.
Bye. Looking through the questions, these are some very interesting questions I can see. So let's continue, if you don't mind. So what metrics are used in determining the efficiency of these tools? Well, I would point out three. First of all is model accuracy. Of course, if it doesn't predict what you want to predict, doesn't matter if it's small enough to fit on your MCU, you're not going to have much use of the model. So model accuracy is one, and according to the correct metric. So the next one is model footprint. It's crucial for tiny ML frameworks, and the third one is model inference time. And all of them are intertwined because, I mean, the accuracy is connected to the size of the model, to the number of weights it builds up. And the footprint is connected, of course, also to the inference time. So the bigger the model, the more computations it needs. So it's really the combination of the three. And as I've shown to you in the presentation and on the platform, Newton provides very accurate models with small footprint. And there is no indication of inference time because we don't know on which device you're going to use it. But you can already understand that with such an accuracy or with such a footprint and with such a small number of weights and neurons, it's going to be quick at inference. So yeah, these are the main metrics. So an interesting question from Sumit. Will we be seeing Newton ChatGPT plugin to allow users to select the best parameters for use cases and start training? Great question, but I believe we've already basically through our demo done just that. We've uploaded there is no text interface, but you've uploaded your data, you selected the target variable, you selected the bit depth of your MCU, and then the platform does everything automatically. It will define all the necessary parameters, and will automatically build a neural network architecture, refine the weights, put it all together in a package that you can download and embed already. So yeah, without the chat interface, it works just like ChatGPT, I would have to say. So how do you work overfitting? We've already discussed. If you want to do ML on the chip, can you further compress the data, say, before sending over BLE? I'm not sure if I, well, I'll try to, two things to answer here. If you are speaking about training a model on the edge, on the chip, we've not been doing that, so we're not working in this direction quite yet. But if you are speaking about inference model on the chip, so yeah, that's exactly what our models are for. I don't know, you just please elaborate a little more on this question. So I don't understand what exactly you want me to answer. Do you have your toolset listed on your page, and are there best practices around updating models and being able to push them over the air? The website, actually the platform, has a quick start guide. It has a very extensive guide with all the examples. Every little button that is on the platform is described with screenshots. So the manual is very concise and clear. So the best practices in there are also described. And push them over the air. Well, I guess if you're speaking about model inferencing through API, we do have this option on the platform, but it's not really is a tiny ML use case. You don't need a tiny model to run on a Google server. It doesn't make sense. But we do have an option of deploying the model into the cloud. There is a separate button and in the predictions tab for some modes of the platform, and you can just test it through the API or inference it through the API if you want that for some reason. Okay, so what are the tools available? Well, lots of tools we've discussed throughout this extensive list of questions. If you could maybe explain what exactly do you mean, because I think we've covered many. So let's go to the next question. Also want to do medical analysis in ECG. Can this be done with it? Actually, yeah, we even have use cases on our platform, on our website. We've trained models to recognize on 2 different data sets for which are comprised with cardiogram data from ECG. So the first use case was to recognize whether the person has arrhythmia or not. The same thing you could see on an Apple Watch. So we train the same model with very high accuracy to recognize whether the person is experiencing arrhythmia. And the second use case, also in the same scope on this similar data, only there are 5 different types of arrhythmia. It's a multi-class classification model. And you have examples on our website with the benchmarks, and you can have a look. So, okay. What are these models deployable for extensive computer vision activities? Unfortunately, no, not yet. Computer vision is out of the scope. How does TensorFlow Lite works? Well, basically, it compresses the trained TensorFlow model through tuning and quantization and transforms it into the format which is acceptable by most modern vendors of MCUs. And yeah, it has its own inference engine, and if you are not careful, even if your model is small enough to fit on your MCU, the inference engine might be much bigger than the flash capability you have on your device. So that's just a few comments on TensorFlow. Of course, there is much more to it. Will it help to pressure-induce treatments by sensing skin sense level? Will it help on pressure-induced treatments by sensing skin sense level? I'm not sure I understand what you mean by this. Well, the generic question would be, if you have some sensor data which differentiates different activities or events, and you have labels corresponding to those events or activities, it's good for machine learning. So I hope I answered your question. Can you explain how Newton framework is able to create neural networks with minimal memory footprint without sacrificing accuracy, and what sets it apart from other frameworks? Yeah, that was the question I answered before. So it's just basically a proprietary built in-house algorithm, which is nothing like traditional neural networks. We don't have a stochastic gradient descent. There is no back propagation and error. The algorithm is unique. That's why the models are so small. So what are some potential privacy and security concerns that could arise when using TinyML solutions in the IoT industry, and how can companies ensure that they are protecting sensitive data? Well, if you're speaking about inference, that's one of the problems that TinyML is geared to overcome. Because when you inference on the device, you don't have to send anything to the cloud. So your private activities, when you're brushing your teeth, nobody's going to know. Only this MCU is going to understand what you are doing and then execute some business logic. If you're speaking about training on your sensitive data in the Google Cloud, well, that is protected by the Google security services. And even us, we don't have access to your data. We can only see the logs of somebody's training something, but the data is within your Google account, and you are the only one, even you cannot access and download it. So it's basically, it's a relation between the user and Google Cloud Service. Can the solution be ported to the Arduino boards or MCUs through Arduino IDE? Yes, it can. And if you go to the GitHub repo that I've mentioned, through that manual, you're going to be porting our model using the Arduino IDE. It's a great platform and we use it all the time. So how are we moving into future of smart wearables and clothing? Will there be a need for legal regulations for such devices? I guess I will struggle to answer the question like this because I'm not a lawyer. I don't know, Blair, maybe you can help me out with this. So once again, how are we moving into future of smart wearables and clothing? Will there be a need for legal regulations for such devices?
Yeah, I'm not sure I can really answer this either. I mean, I think for the most part, a lot of personal and health information is already captured with your, your phone, your smartwatch, whether it's a Fitbit or anything of the sort. So I don't know if I'm, qualified to answer that question. I'll say it that way.
All right. Okay, so the next one is, can you explain how Neuton framework is able to generate neural networks in minimal memory footprint, and what is the importance for devices with limited resources such as NicholasSense ME? Well, NicholasSense ME, just frankly speaking, is not very much limited. It's a powerful device with Cortex M4. How the model has been trained to become so tiny, we've already elaborated. And why is it important for devices with limited resources such as NIC? Well, in general, this device is going to run somewhere on a battery. It's not going to be connected by a wire to the power. This is just for the demo. So like in the smartwatch, it's running from the battery, and you have to charge it every day or every 2 days. So this is the main challenge that you have to overcome with these models, even if they can fit onto the MCU. How much memory, how much RAM, how much energy is going to consume running all the time, always on. So, I mean, even if it fits on the MCU, you still have to make it as small as possible, because running real time, all the time, 24/7, trying to predict what you are doing is going to consume more and more battery. So the main challenge is just to make them as small as possible. Even if the threshold of fitting into the MCU is way above, they still have to be small. Okay, so what are the steps for creating this model with TensorFlow, please? Well, I briefly mentioned, so first of all, you'll have to define the neural network architecture. Then you have to process your data accordingly. Then you will train and validate your model with your first iteration of the architecture, and you figure out what is the accuracy provided by this model. Of course, when you define your architecture, you'll have in mind the restrictions on your MCU, and so that's why you will be limited by the number of layers and nodes in the neural network. You'll be adding dropout, and well, that really doesn't matter. So it's going to be a first attempt. If you are very extremely lucky, you will create a model that satisfies your accuracy needs and is small enough. If you are not lucky, which is true for 99% cases, you will go to build different architectures. You will try different activation functions. You will try different number of nodes or different number of layers with nodes. And through extensive iterations, you will basically do either manually or automatically neural network architecture search within the boundaries of your MCU memory footprint. So after you will have found your, and this will take time, you will need a GPU, you have to be qualified to do that. So after you will have created the model that satisfies you in terms of accuracy, you will then have another challenge. It's not really a challenge, it's a technicality to convert it into TensorFlow line. But in our experience, we've had quite a few cases that after conversion, it loses 15% of accuracy. So because you naturally, when you compress the network, you remove predictive power, you remove the knowledge through pruning and quantization, other techniques. So you're gonna have to test it again. It doesn't happen often, but it does happen. And on average, it will just slightly reduce the model accuracy, but sometimes it can be as much as 15%. So these are the challenges. And then after you compress it to TensorFlow Lite, then you have to figure out a way how to embed this into your MCU. So you're gonna just have to read the documentation, extensively read the documentation of your TensorFlow Lite of your MCU to be able to embed that on that device. With our archive, there comes a README, and there's also comes 24/7 support that are going to help you do that. All right, so I hope I answered the question. So the next one is, I'm working on an application for elderly people monitoring. I'm very interested in what you showed. I would like to try and repeat this. Great. Let us know if we can help. I guess there is no question here, but yeah, that's a common use case. By the way, we are now working on a model for the younger generations. So, well, actually it's for everybody, but you have to control how thoroughly have your kids brush their teeth, right? So we created a model that will, when placed on a toothbrush, that will detect which of the 9 areas of teeth you are brushing right now, and how much exactly have you been brushing them. So if it is required, according to the medical procedure, to brush your teeth for maybe 20 seconds, your front teeth, then upper left teeth, upper back front teeth. So there are 9 areas altogether. We've trained a very good model. We have a very interesting and visual demo. So even such subtle differences between your upper front teeth and upper back teeth are recognized by a Neuton model. And basically you can brush your teeth and it will just visually on your mobile phone will show you how thoroughly have you brushed each area of the teeth and which you need more attention for. So, okay. How will the screen be when the Opta breaks down, and what could be possible solution to it? I'm not sure that I understand what you mean by that. Please elaborate what is Opta and what is a screen. And and how I can help, because I don't understand this right now. So how fast is the motion sensing capacity of the neuron? So if you're talking about the model inference time, of course, it depends on quite a few things. As I mentioned, the actual model size, so how complex is the model? Say if you're training to predict what I've just shown to you, there is 1,000 weights, so there is an X amount of iterations that has computation that has to be done on inference. If you have 10,000 weights, so that's 10,000 times more computations that you have to execute. So it depends on the complexity of the problem and a subsequent model complexity, model size. Also, it depends on the digital signal pre-processing functions selected for this particular signal. If you went on our platform and selected all of them, so that means that when the raw signal arrives, you have to extract many different features. And some of those functions, like for, say, spectral features extractions, are quite heavy on the computation. That will increase the inference time. You always have to find a balance, and the platform is configured by default with that balance in mind to create small and accurate models. But of course, it's in your control even to deselect more features or add additional ones. So I hope I answered your question. Can we collect our data from the accelerometer ADXL335 sensor and Arduino to create our own data set? Well, yeah, you can collect your data from any sensor. as long as you be able to then fit the model onto that device. And we have good examples of and live demos of running our models, not on MCU, but on a sensor. And this makes the overall application much more efficient, because you say you want to predict a person falling, right? So on your watch, it's going to be running 24/7 on that MCU, processing what you are doing and understanding when you have fallen. But if it's running on a sensor, and hopefully you will never fall in your life, it will never wake up the MCU and tell it that you have fallen, call 911. But if you have happen to fall down, only then it will wake up the host MCU and will just tell it to execute some business logic. So that's the advantage of embedding models straight on the sensor. Okay, so how fast is the motion? Okay, we've discussed that. How is acceleration supported on non-proprietary frameworks and libraries besides TensorFlow, PyTorch, and POC? How is acceleration supported on non-proprietary? I'm not sure if I understand what you mean. Acceleration of what? So accelerometer data? Well, really, regardless of the final algorithm, whether it's Newton or TensorFlow, you have to process the data from accelerometer to be able to inference, to recognize some kind of activities. So I'm not sure if I understand the question correctly, but I mean, with accelerometer data, you can train any model. It just depends on the effort and the final outcome. So just let me know if I missed something. How regular are framework versions capabilities updated? How regular? So if this is a question regarding our release cycle, it never stops. So we always add additional capabilities. And so in the previous time, we've recently we've added additional feature extraction and feature selection capabilities. There is always constant week after week improvement to the platform. I would say every month something changes, but nevertheless, the core technology stays the same. Hi. Okay, so how much time did it take to build the hand activity recognition project? Well, as you've seen from the live demo, the actual model training took 1 hour and 43 minutes. And after that, there is nothing else you have to do, or then you just download the archive and you can embed this into your MCU. But the overall project, of course, depends on your capability to collect the data. And if you want to build a good enough model, you need to collect the data from different subjects, with different hand motions, so that it would be robust, so that it could generalize on out-of-sample population. Like in this case, on myself, when my data was not used for training. So I would say the majority of the problem in a TinyML or any machine learning use case is the data collection. Once you have that settled, or if you already have a data set with the platform, all you have to do is upload it, define the parameters, and just go about your business. And we'll send you a text message when it's done. Usually from hours to a day, maybe if it's a very big data set, but you are not going to waste any of that time. It will do everything on its own. What sorts of accelerated computing does Neuton.AI support? Well, GPU, and depending on your data size, an appropriate number of GPUs are going to be deployed for training the model. And this will happen behind the scenes on the back end. You will not even notice any of that. So yeah. How can models be ported out of Neuton to other frameworks and libraries? Well, first of all, it's C code. You can basically just open the model weights in the file, which you can download from the platform, and see them. And there is really not a lot of them. And you can open the inference engine, which is basically a script that is going to apply those weights to your input data. And you can open the scripts for digital signal preprocessing. So everything is open to you. That's for one. So you don't need other framework to inference the neural model. But also we've been working on, for some specific vendors, they have a requirement to run the models on their devices, that the model will be in TensorFlow Lite format. And we've went through some extensive R&D and found a way to port or to push our model inside the TensorFlow Lite framework. It's not advisable because it loses some of its beauty. but it's possible, and we have solutions for that. What advanced generative or GAN models are available on? No, the GAN models are not available on Neuton. It's a hot topic these days, but yeah, that's the use cases that we are working with in a tiny ML space are not very much or in any way connected to the general adversarial networks or generating some additional data. You have to interpret the sensor data, and there are numerous applications. Everything is IoT now. So a GAN model for IoT, I really don't know how could it be used. So to detect running accurately, I should only give the sensor running data, not data from other activities like walking. No, that's that would be, because if you give one example of one activity, that's the only thing the model is going to be able to record. It hasn't seen any other data. That's why in our example, we've added an extensive data set of random activities, things like that, or maybe speaking on the phone, or drinking tea, or just sitting idle, typing on a computer. All of that is an other class, not what we are looking for. And that's a separate class. And the model will build neurons and ways to understand that these types of activities are this class, a random class. So in your case, if you want to distinguish running, walking, jumping, sleeping, and these are the 4 classes you're looking for, you have to actually collect 5 classes. So data for 4 classes and everything else. And this has to be a diverse class, laying down, standing, I don't know, commuting on a bus, because all of that, you don't want when you are riding on a motorcycle for the model to detect that you are running. You want it to detect an other class. So you always have to have a random class, regardless of the number of actual classes you're looking to recognize, because in the vast majority of time, the model has to predict this other class because you're not running. Okay, does Neuton support other forms of advanced computing besides machine learning? Well, Neuton is a machine learning framework, an automated machine learning framework. So yeah, I guess no. While training the data, does the Neuton patented framework employ all same neural operations? Well, the architecture is going to be unique for any problem. And if you take the same data set and remove just one record out of it and train a model, like once again on the platform, you might have a very different architecture, a result of the resulting model. So,
so Daniil, just one last, let's pick one more and then close out, because we have, let's say, doubled our time. We're now at 2 hours. So maybe if you would like to kind of breeze through the questions, find one that you find maybe the most intriguing, or one that you haven't answered already, and then let's pick one and then close out today's discussion.
All right, so does Neuton employs noise injections while training? Well, the data set before you upload it to the training has to be complete, and it has to include basically all the different scenarios you want the model to understand. So that means if you have sometimes noisy environment in your activities, like you want to detect, I don't know, drinking tea, but if you are riding on a motorcycle when everything is shaking, you're trying to do the same and you want to predict that, that's a noisy environment. That means you have to have examples of that noisy environment correctly labeled. That within this environment, this action, regardless of the fact that you are shaking from the motorbike, is drinking tea. So you cannot inject data after the training has begun. So it's a matter of you collecting and preparing a representative data set to the environment you want your model to operate in. If it's in perfect conditions, so then it is no noise. If it's not, you either collect the data for different environments of the same activity, or you collect the data in one environment and manually add noise to multiple techniques. Thank you, guys. There was a lot of great questions out here. It's quite a challenge to answer all of them. I'm sorry to those who we've missed, but yeah, we went an hour over our time.
But
So
we
just-
will count your questions that already appeared now in Q&A session. Okay, so no worries, you will be participating in giveaway. And don't forget, please, to register on our platform. It's a second condition to be a part of our giveaway. I think, yeah, Blair, you answered in the chat. So please check if your account is active by now, by tomorrow, when we will be making the selection. And yeah, thank you so much to be with us this evening, this morning, this day. Thank you so much, Daniil and Blair. I saw a lot of great words to you, because you did a very great job answering so many questions today. Thank you, ZG. I hope you will join us many times in the future and bring more information about sensors. That is very interesting now. From my part, I really happy. We're very happy to be with you guys. So see you soon. Please join Slack, like us in LinkedIn, and we will be very happy to help you in your projects.
Thanks, everyone.
Yeah, Blair.
Thank you.
Thank you, and thank you all team that helped us to organize this amazing webinar. Thank you so much. See you soon.
Thank
Have a
you.
nice day. Have a nice week.
Thank you
Bye.
very much.
Thank you.
Take care. Bye.